Mars 101, I'm not going to assume you all know what Mars is like. So, Mars is a little bit smaller than the Earth. It's about half the size, but because the Earth is predominantly ocean, in terms of surface area, there's about as much land to walk around on Earth as there is on Mars. There's as much exploring to do there as there is here. It's about 50% further away from the sun than we are, so it means it gets about half as much solar energy as we do. Its year is twice as long, so we go around the sun in just over 365 days. It takes Mars 690 or so. And a Mars day is similar to an Earth day, but slightly longer. So if you're operating a spacecraft on Mars time, you have this 40-minute or so break every single day. So if you're operating on Mars time, you might have a meeting at 12 o'clock Mars time today. Tomorrow, that meeting is going to be at 12:40. Then it'll be at 1:20. Then after, it'll be at 2 o'clock. 2 weeks later, that meeting's in the middle of the night. And then 2 weeks later, it's back where you started again. And if you're operating 2 spacecraft on Mars and you transition from one to the other, you get Martian jet lag. It can really, really screw with your mind. A lot of people think Mars, they think red, they think it's hot. It's a commonly held misconception, especially in school kids for some reason. It's not. Average temperature on Earth is about 10 or 20 degrees centigrade. On Mars, an average temperature is about minus 80 degrees centigrade. On a particularly balmy summer equatorial day, Mars may get to perhaps 15 or 20 degrees Celsius. Most night times, especially near the poles, minus 140 degrees centigrade. It is a cold and very nearly airless place. There is an atmosphere on Mars, but it's predominantly carbon dioxide and it's very, very thin. Now, there is a place on Earth you can go to that's pretty much like this. That may be minus 50 degrees centigrade and about 10 millibars of pressure. If you can beg, steal, or borrow a U-2 spy plane, fly it up to about 100,000 feet and open the window, and 2 things will happen. 1, you will fly out the window and so will everything else inside the cockpit. But 2, the temperature outside is about minus 50 degrees centigrade, and the air pressure at 100,000 feet is about 6 millibars. This is what Mars was for tens of thousands of years. Mars is a planet. Planet means wanderer. This is what the ancients called these stars that appeared to move. Mars, when it's close to the Earth, is one of the brightest things in the night sky. Here you can see the Orion constellation. And this was all we saw of Mars for thousands and thousands of years until the advent of the telescope. Now, next year is the International Year of Astronomy, which is actually scheduled to record the 400th anniversary of the discovery, or the invention of the telescope. And until we had telescopes, until we pointed these telescopes at Mars, all we had was just this red dot that seemed to move across the sky. Telescopic views, particularly in the 19th century, turned Mars from just being this little red star into being a place that people could study. It would turn into a little world. And this is your average telescopic view over a whole evening of what Mars is like. And to date, with an average-sized telescope, you're unfortunately not going to get a view much better than that. The observatory just down the road here, looking at Mars, you're going to see something about this good. Late 19th century, an Italian astronomer called Giovanni Schiaparelli studied Mars, and he was looking at Mars at about this sort of quality, and he drew a map. And you may not be able to see the legend here, but he's described these white areas, which are the kind of the beige areas here, as being land, and the dark areas as being perhaps water. They're written here in actually translating the German Wasser, which means water. He was so wrong, but it was his best stab at what he could see. He wrote down that he thought he saw things called canali. Now, he was talking about channels, natural channels. An American astronomer called Percival Lowell, a couple of years later, read Schiaparelli's work, spent a fortune on building an enormous telescope to go and look for canali, thinking they were canals. And Percival Lowell wrote at great length on the demise of this complex Martian civilization that was becoming barren and dried out, and they were spending all their efforts building these vast canals to transport water around the surface of Mars. But this really, until we actually went to Mars, was all we had. Very, very rudimentary maps and a few little pieces of information. Unfortunately, our first speaker had to cancel on us, but he was going to be talking about the Falks telescopes. And the Falks telescopes are pretty epic research-sized telescopes. That's a picture taken with one of them of Mars. It's pretty small. They're not good telescopes for looking at planets, but this is sort of your average big telescope view of Mars from Earth. So it took until the space age until we could really get a decent look at what this place was about. Getting to Mars is damn hard. It's a very, very long way away. At the very closest, the Earth and Mars are perhaps 30 or 40 million kilometers apart, but you can't just point a rocket, travel 30 million kilometers and be there. The best effort you can get is to fling a spacecraft with a fairly hefty rocket and spend between 6 and 12 months cruising all the way out to Mars. You spend all the time just drifting through space. As a result, you actually end up traveling perhaps 400 or 500 million kilometers. That's like going to the moon and back 500 times. It's kind of 10,000 laps around the Earth. Once you get there, you've got another challenge. Not just traveling this far, not just getting off the ground, traveling through space, but you've got to be accurate when you get there. Here's a picture of Mars, and to scale, roughly speaking, a tiny 10-kilometer target. This is the sort of size accuracy you've got to have if you're going to successfully land on Mars or you're going to successfully enter orbit around Mars. You've got to hit a target about 10 kilometers across after flying 400 million kilometers. To give you a sense of scale, that's like standing here in Milton Keynes and hitting one of these that sat on the top of that. It's a targeting challenge like no other. And I can tell you that recent spacecraft are hitting this target here, not with an accuracy of 10 kilometers, but the most recent actually hit with an accuracy of 800 meters, so less than a tenth of that. We've been exploring Mars for about 48 years, and the Russians tried first. This is the Mars versus Earth scorecard, and to begin with, it makes pretty horrific reading. Failure, 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 failure. It gets better towards the end. One notable case, unfortunately, is a spacecraft that was built, was conceived, built, and started its journey to space, technically from here in Milton Keynes, Beagle 2. Beagle 2 is unfortunately the only failure this century. From 1960 to 1999, if you launched a mission to Mars, 3/4 chance it was going to blow up, crash, miss, fail completely. One particularly horrific situation, Russia in the 1970s, 1973, in a period of about 3 weeks, they launched 4 spacecraft to Mars. 2 of them completely missed. One of them went into orbit and died 9 days later, and one of them crashed whilst trying to land. That was just 1 year's effort. NASA has done much, much better. It had 1 failure early on, some pretty good results here. These are the first landers on Mars. It had a failure here and had a horrific time in 1999, but it's doing much, much better more recently. So kind of the modern success rate is more like 85%, with Beagle 2 being the only blot on our copybook. But the Viking Landers back in the 1970s were hugely expensive. They spent the equivalent in modern money of something approaching $4.3 billion to put 2 spacecraft onto the surface of Mars and take pictures like these. And NASA wanted to go back to Mars in the 1990s. After the 1970s, after the results of this barren terrain, they went along looking for biology and they came up kind of blank. And so Mars wasn't sexy anymore. It was fascinating back in the 60s and the 70s. They got this far and they thought, what's the point? There's nothing really exciting here. 15 years later, the scientists had a chance to digest all the information collected in that period and found Mars actually geologically was a fascinating place. So they wanted to go back. They wanted to go back with lots of spacecraft and land on Mars perhaps a dozen times. And so to do that, they wanted to find a new, cheaper way of landing on Mars. But landing on Mars is really, really hard. Mars has got an atmosphere, and it's not very thick, but it's thick enough that you have to take a heat shield with you. You've got to take a heat shield the same way you need a heat shield to land on the Earth. And you're going to go from Mach 25 to about Mach 2. You're going to decelerate at about 12 G, have temperatures on the outside of about 3,000 degrees centigrade, whilst a few inches away inside is room temperature. Once you've done this bit of the fiery re-entry, you can deploy a parachute. A supersonic parachute is not a simple thing to design. NASA is the only people to successfully do it to date. To get a sense of scale, here is your generic NASA engineer. These things are absolutely enormous. But even with an enormous parachute and not something particularly heavy on the other end, you're still going to be doing 200 miles an hour. And I'm not going to crash my laptop into the ground at 200 miles an hour. You're not going to crash a $400 million spacecraft into the ground at 200 miles an hour. So you try and protect it. You wrap it in airbags. It's like the airbags in your car, but much, much more expensive. And just to take the edge off that 200 mile an hour impact, they take along some rockets as well. Very dumb, simple, solid rockets that would fire at the last minute, take away some of that speed, so that if you combine all of these into one complex Mars Pathfinder mission, you get a bill for about $280 million. Now, this was before NASA took into account full cost accounting, and you can add about 50% on that in terms of unaccounted overtime. Mars Pathfinder was a beautiful success. It was the first internet phenomenon. In fact, Mars Pathfinder in the summer of 1997 brought the entire French internet network to its knees. Too many French people were looking at pictures like this. The whole thing crashed. This is a place called Aris Vallis. From orbit, it looks like an old floodplain. You can see craters that have tails behind them where water has flooded through in the ancient Martian past. But the most important thing Mars Pathfinder did was not these pictures. It was proving this new landing system would work, and it did, quite obviously. It was also the first time that a vehicle was sent to another planet. The Russians had sent rovers to the moon, and you can sit in your office and drive a rover on the moon with a joystick just about. This is Sojourner. This was the first robot to drive around on another planet. Here it is in a photograph before it was launched. When you go to Mars, you can't sit at your desk and use a joystick. If you did, sit there, you push the joystick forward, and it's going to take 4, 5, maybe as much as 20 minutes for that signal to get to Mars. You've been holding the joystick forward for 20 minutes. By the time that your signal gets there, you've got 20 minutes of driving forwards all going there. It starts driving forwards and it starts sending you back pictures. So 40 minutes after you first hit that joystick, you get the first semblance of an image that it's moved. You see a massive canyon, you let go of the joystick, too late, 20 minutes ago you drove over the edge. So you can't sit at a desk and drive a rover. What you have to do is do some programming. You have to be intelligent. You have to put intelligence inside this little rover. And on the NASA scale of objects, this is a microwave-sized rover. And you have to command a whole sequence for one day in advance. You put some intelligence in the rover, and using the intelligence of the engineers, they'll actually write a sequence to tell the rover what to do in one day. And because Sojourner drove out from this lander called Mars Pathfinder had cameras so it could see Sojourner doing its little thing. And here you can see it trundling its way around Mars. It's nothing if not cute, to be honest. It is putting a little wheelie. It had a science instrument on the back called an alpha particle X-ray spectrometer. It didn't do a great deal of science. It was a technology demonstrator. And what it proved was that we could do roving on another planet. We knew how to do this stuff. We knew how to do this 6-wheel drive, 4-wheel steering, rocker bogie suspension system. And it worked beautifully. It even had little cameras on board, had black and white cameras on the front, and a crummy little colour camera on the back, a colour camera that's way, way worse than anything any of your mobile phones have got. They really are pretty rudimentary. You can see the horizon and a bit of a rock here. Here you can see a rock that actually it's deployed this little instrument onto. The black and white pictures in the front are a little bit better. Here you can see the empty lander, and from a little bit closer you can see the empty lander and its camera mast sticking up at a bit of an angle there. So Mars Pathfinder, a beautiful success. NASA decided, right, we're getting Mars right. Let's go every single time we can. You can launch to Mars every 26 months. So let's go every single time. And every single time, let's send an orbiter and a lander. So 1999, we're going to send the Mars Climate Orbiter and the Mars Polar Lander. Mars Climate Orbiter was an operational failure. What that means is that the people on the ground screwed up. They crashed it into Mars. It's that simple. Instead of hitting that window of 10 kilometers just outside Mars to go into orbit, they ploughed straight into the atmosphere and the spacecraft burnt up. The root cause was a managerial problem. People weren't talking to each other well enough. The people who built it weren't the same people who were operating it and weren't the same people who were receiving data from it. People didn't talk to one another, and various complex engineering reasons it diverged from where they thought it was. And by the time they realized there was nothing they could do about it. Mars Polar Lander, well, we didn't really know why that failed at the time. It took some months to figure out why it had just started its entry and we never heard from it again. In some respects, quite reminiscent of Beagle 2, but kind of in advance, as it were. Some months later, the root cause was found, and it was a programming error. But a programming error that, again, found its root cause in the same kind of reasons. The big picture was that they were trying to do all of this far too cheap. They tried to do this whole lot for less than they spent on that one Mars Pathfinder. This led them with a problem. They'd spent a couple $100 million here, absolutely zip to show for it. 2001, they were planning a very nearly identical orbiter with a laser pointer that's died. Sorry, John T, I've killed your laser pointer now. And a lander that was very nearly identical. Now, we knew why we'd crashed the orbiter. We drove it into Mars. It's a pretty fundamental thing to be able to fix. The lander, they didn't really know why it had failed at the point at which they had to make a decision, do we cancel it or not? And they decided to cancel the lander. The guy who was designing the instruments for this, a gentleman called Steve Squires, has actually given a lecture here. He was 6 weeks away from delivering a calibrated payload to be put on top of this vehicle to go to a place on Mars when it was cancelled. He'd actually submitted proposal for instruments for Mars Pathfinder and Polar Lander and was successful with this mission, his third try, and it gets cancelled 6 weeks before delivering his instruments. This is a challenge for 2003 because where do you go from here? You've got a landing system that worked back in 1997, and NASA have been wanting to send a big rover to Mars for years and years and years. They had ideas. This is a test rover on the Earth called Fido. They had others called Rocky 4, Rocky 5, Rocky 7, lots of different designs for rovers. And they had the instruments. They had instruments from that cancelled lander. And so what the scientists at the Jet Propulsion Laboratory in California did is crash all of these into one another, put these instruments on the rover a bit like that, and hide it inside this landing system, and come out with the Mars Exploration Rover. And with that, you get a price tag of about $440 million. This competed as a proposal against a very large orbiter that was due to launch in the same 2003 timeframe. And the decision was delayed. People were waiting to find out, are they going to fly the new cool rover, they're going to fly a big, safe orbiter. The decision was delayed because this proposal had gone to NASA headquarters, and this chap, who was the NASA administrator at the time, has said, I don't want to fly one, can you build two? And the engineers had about 90 minutes to go away and figure out how much a second one was going to cost. And at the time, they thought it's going to be about buy one, get one half price. By the time they launched, engineering problems with parachutes and airbags and onboard systems meant that $665 million budget actually was completely roasted and turned to a budget of about $820 million by the time they launched. That's for two vehicles, which actually is not too far off being twice what they thought. This is the vehicle they built. They called them Spirit and Opportunity. I can't tell you which this is. They are identical in just about every single way. If you unbolted things and found some serial numbers, you might find some differences, but that's about it. These vehicles are covered in cameras. They have navigation cameras, some at the top here, and some wide-angle, googly-eyed cameras at the bottom here. They've got beautiful panoramic cameras that take these amazing color pictures that you can view on the web. And there's a microscope on the end of the arm. And there's another camera that's actually bolted to the lander that brings the whole thing to the ground, and that takes pictures on the way down. There's also a thermal emission spectrometer. This is a kind of a spectrometer that can identify minerals at a distance as well. So this is the thing actually landing on Mars. This is from a movie called Roving Mars, and is a reconstruction of the landing of Spirit from actual data reconstructed after the event. So we've got our fiery re-entry from Mach 25 down to about Mach 2, screaming through the atmosphere towards this, which is a large impact crater. Throw out your supersonic parachute, falling through the sky at 250, 220, maybe 200 miles an hour, falling towards the surface. All this happens very, very quickly. It's 6 minutes of absolute terror, and the engineers are completely hands-off. They have no control over this entire procedure. You get rid of your heat shield, you don't need it anymore, and then the lander, with its undeployed airbags, is rappelled down a large rope, and so now you've got the parachute, the back shell with its little motors, and the lander. About 5 seconds before you hit, you inflate the airbags, the radar locks onto the ground, and when it thinks it's just about to hit, you fire the rockets, and you bring the whole lot to a dead stop about 5 meters above the ground, after a journey of about 450 million kilometers. And then this thing bounces, and it bounces high, it bounces very hard, and it bounces for as much as a minute. It bounced about a dozen times, and about 4 stories high. But eventually you roll out, this looks ridiculous, but it's actually, because of the low Martian gravity, what it would actually look like. And this is imagery reconstructed from the lander itself, showing what the event might have looked like. You come to a standstill, you deflate the airbags, you open up the lander, and you deploy the rover from inside. So where did they send them? Well, they sent Spirit here. This is Gusev Crater. It's a crater about 100 kilometers. But what's remarkable about it is that it's a crater with a great big river flowing into it. So suggesting that this was once a very, very large lake. They opened their eyes, and these were the first pictures they took. They're expecting to see sediments. If you get a big lake, you get sediments forming in the bottom. And if you can find these sediments in situ, if you can find bedrock or in the walls of a crater or original pieces of sediment, you can read this sediment as a record of geological history. You can understand what went on in this place long ago in the past when it's conjectured the place was much, much wetter than it is today. They arrived at Gusev Crater, and every single rock they could find wasn't a piece of sediment, it was just a piece of lava. This is a rock called Adirondack. It was the first rock they went to look at. They put all their instruments onto it, and it just turned out to be an ordinary piece of basalt. Nothing exceptional at all. This is a major blow because they went here looking for one thing, and that thing just was not there. They left their empty lander there. Here you can see the bits of airbag left over. And the rover itself was actually all tucked up inside this tiny little base petal here. Drove off from here. The good thing about a rover is if you don't like where you are, you can move. And so they did. And in fact, here you can see the rim of a crater, which is this crater here. And here you can see the beginning of some hills that they called the Columbia Hills, named after the lost crew of the Columbia shuttle, which was lost only a few months before this thing took off. And they decided they were going to go to this crater, which they did, from where they landed, and hoping to find sediments in the walls of this crater. No cigar, nothing there at all. And this vehicle is designed to last about 90 days and drive about 600 meters. 90 days was about here, and they thought, what the hell, foot to the floor, and they tried to make out for these hills down here, 2.5 kilometers away, which is what they did. And after 154 days, they crossed over from the terrain on the floor of this crater to the hills, and everything changed in the space of a single meter. By the time they got to the hills, the front right wheel was beginning to act a little bit arthritic. It was putting a bit more current than the other motors, and they were nervous about using it too much. So they ended up climbing the beginning of these hills backwards using 5-wheel drive, saving that motor when they really, really needed to use it. But after a lot of struggle, you can see they're churning up the ground a huge amount here. Having climbed all the way up from the foot of these hills, the lander is way off in the distance here somewhere. They eventually made it onto kind of the escarpment of this range of hills called the Columbia Hills. This is an area called West Spur. And to give you an idea of what sort of angle they're driving at, look at what angle these frames are at to give you a flat horizon. The rover is kind of off at an angle like this. But the rocks here were completely different to the ones out on the plains. You can see just down here, they actually used the instruments on the arm to drill a little hole. And these rocks were not just ordinary lava. These rocks were formed in the presence of water. They had a mineral called Gerra Site that forms almost always in the presence of water, suggesting there was water in this place. Once they got to the very beginning of the Columbia Hills, just here, they decided they wanted to get to the absolute summit because, you know, you can't go to hills without climbing to the top and having a look around. And you can see here, here's the pattern of them driving backwards with 5-wheel drive. They would drag that one wheel time after time and then just drive it for a little bit to clear the lump of a trench they dug, then drive it a little bit, start dragging it. But over time, purely by driving backwards, they redistributed the lubricant in that wheel and essentially kind of saved itself. It became much, much better, and they began to be able to use it again. And they really, really needed it to climb this hill. By this point, about 300 days into a 90-day mission, Spirit was looking pretty dirty, pretty filthy. Dust falls out of the Martian atmosphere all the time. If you hang around long enough, you're going to get caked in it. This is what Spirit was like, and was getting to a point where it was very, very low on power, so low that much more of it, and it would have actually had to turn off and die. Pure good fortune, this happened. In the foothills of the Columbia Hills, just the morphology of the terrain, lucky gusts of wind blew almost all that dust clean off the solar panels. At about the same time, they had their cameras looking off across the plains, and they saw these. These are dust devils. These are baby tornadoes on the surface of Mars. Here's some more of them. Oop, I've skipped. I'll go back again. These images are about 20 seconds apart. They have taken hundreds of movie sequences like this and have observed thousands and thousands of dust devils. These are a lunchtime phenomenon. They're a summer phenomenon. And they don't think that one of these actually cleaned the dust off the solar panels, but kind of the general fast winds associated with conditions like this are what have kept the solar panels clean and kept the vehicles alive. They got to the summit of what they called Husband Hill. They named the biggest hill in the range from the commander of Columbia, called Rick Husband. And this is a view all the way across the summit. To give you a sense of scale, in terms of resolution, to show this picture in full resolution, you need 3 IMAX screens. They run at about $10 million a piece, so I don't recommend it. You can print these at 300 dpi at 60 inches across and still be needing more paper. They're absolutely enormous images. Here you can see where they've arrived and they crested them on the summit. In fact, using a program called Midnight Mars Browser, which is a free program written by some enthusiasts, you can actually see the drives that they took on the summit of Husband Hill. If you're wondering what this funky little feature here is, it's a kind of a green streak and a red streak, and you may even be able to see a blue streak as well. When they take colour pictures on the surface of Mars, they don't have a colour camera. It's a black and white camera, but they use filters in front of it because you can get much, much clearer pictures if you do it that way. And in between taking the red picture, the green picture, and the blue picture that you then put back together again to get the colour, a dust devil sailed past, and so the dust devil was here in one filter, and here in the next filter, and here in the last filter, to get these funny colour patches. They took a look off towards the south after they looked at the top of the Husband Hill, and saw this strange feature here. It's about 100 meters across and much, much brighter than the terrain around it. They called it home plate because, being Americans, they love baseball. And over the next couple of hundred sols, they drove off the summit of Husband Hill and all the way to this feature here. But at this point, they had huge amounts of power while they were on the summit of the hill during their second Martian summer. But summer very, very quickly turned to winter, and dust very, very quickly accreted onto the solar panels, and it was a sprint to get from here, quickly look at home plate, and the plan was try and get up here to the next hill along, so they could spend the winter sunbathing on the north-facing slopes of this next hill along. Before they did some astronomy. You might not be able to figure out what that is. Here's another one. And here's the other one. Mars has got 2 moons, but they are very, very small. Phobos and Deimos. They're kind of Anglesey, Isle of Wight-sized lumps of rock. Phobos is much, much closer, and here that's Phobos crossing the surface of the sun, and here's Deimos, much, much smaller. That's already gone. For amateur astronomers amongst the audience, a Deimos transit actually looks a bit like a Venus transit, but it's much, much quicker. They tried to get to this hill, the next hill along, to get some sunbathing for the next winter. And just before they got there, in a kind of a sandy patch of ground, that front right wheel came back and failed completely. They'd had an extra couple of years out of it on this 90-day mission. Eventually, it gave up the ghost, and you can see it churned up huge amounts of soil. And this is a pain because they couldn't get to the hill that they wanted to get to. They had to retreat back to a safer place. But at the same time, they've now got this kind of non-optional trenching tool. Wherever they drive, they drag a trench through the ground. And by chance, they dragged up these enormous amounts of sulfate deposits. These are Epsom salts just underneath the Martian soil. And I'm getting to a point in the story for Spirit whereby the story is ahead of the scientific understanding, but the conjecture is that home plate itself is actually a volcanic feature, and that these sulfates here are as a result of water or water vapor interacting with that volcanic activity. They retreated to a place called Low Ridge Haven, a slight slope they could park on for their winter. In fact, you can see the mess they made over here. And after about a year camping here for the winter, they got moving again and headed back towards home plate, and they did more trenching accidentally and dug up vast quantities of silica. And the form of silica they found here, we're talking 85% by weight silica in these soil deposits. That's an almost surefire indicator of water on volcano action. This stuff is very, very indicative of water in and around this feature, hot springs, that sort of stuff. Think kind of Yellowstone National Park. Pretty extraordinary geology. That's where Spirit was on its winter haven. This is from a camera called Highrise. In fact, that picture Jonty showed of that crater is taken by a camera called Highrise. Now, if Highrise was in orbit around the Earth, its pictures would be classified. Google recently sponsored the launch of an orbital mission to the Earth that's taking pictures at about 40 centimeters per pixel. So your average pixel is about this much ground. US defense law dictates they must downsample that to 50 centimeters per pixel before they can release it to the wider public. The US military is not happy with people having pictures of the Pentagon, the White House, or, Edwards Air Force Base at 40 centimeters per pixel. This camera takes pictures at 25 centimeters per pixel, twice as high as the US military would allow you to see of the Earth. And it's not just looked at Spirit once, it's looked at Spirit. There is the actual rover, and it moved a little bit. It moved a little bit more. And it moved again. Just onto the edge of home plate. A local dust storm completely obscures it. Reappears here, drive down to here, all the way around to here. And that is where Spirit is today. And in fact, Spirit has been sat in the same place on home plate for a couple of hundred sols. That little speck is Spirit itself. Yesterday, quite literally, after hankering out for the entire third Martian winter, barely surviving on the power it was able to generate, Spirit drove for the first time yesterday morning after about 200 days. This is the view from the north of home plate. It's taken the whole winter, 200 days or so, to build up a panorama. It's not all come down yet. It has been all taken, but it's not been all downlinked to the Earth yet, of the whole 360 degrees in every filter and very, very low compression. To give you an idea of what that move is like, this is from the front of the rover. The front wheels are here at a big angle. And just that little move there, from there to there, get a bit of a reference. See that little rock there? It's moved from there to there, moved about this far. That's the first move for about 200 days. Just hankering down, trying to survive winter, sunbathing, facing north. But what this also is very, very good news, because it means Spirit, with that front right wheel that's actually broken, it will be able to climb back up onto home plate. They weren't sure if, after getting off the edge of home plate to get this solar power, whether or not it would be able to climb back up, and whether or not it would have to scoot all the way around. And that first little drive shows that actually we'll be able to drive back up onto the top of home plate and explore two features just south of home plate that look like lumpy versions of home plate, perhaps different types of volcanic geology. To give you an idea, this image was taken at 2:15 this morning. This image was taken actually the day before and shows Spirit just looking out across the edge of home plate. Look at the angle on the horizon there. It's about 32 degrees. That's the angle Spirit has had to sunbathe the sun being lower in the north during its winter. And this small drive's taken a few degrees off that. It's a little bit flatter, but still trying to get as much solar power as it can. It is very, very low on power, but it has survived its third Martian winter. And with limited mobility, they're going to head off back across home plate and look at interesting geology to the south. Meanwhile, on the other side of the planet, Opportunity was sent, the twin rover of Spirit, and it was sent to what is probably the only remarkable feature in this entire map, which is this funky little patch here. This is a map made by another spacecraft of minerals, in particular one mineral called hematite. Some of you might have seen hematite jewelry. It's an iron-bearing mineral that's predominantly formed in water. Not always formed in water, but usually formed in the presence of water here on Earth. And with one tiny little patch of it on the whole of the planet, they thought that might be an interesting place to go. This was the landing ellipse just here. This is the safest part of that hematite they could find. Same landing system, same launch on a similar rocket. Here's the actual trajectory reconstructed after the event of Opportunity, coming in on its parachute, firing its rockets and bouncing across the surface. These three pictures here are the three pictures taken by the spacecraft on the way down. This little dark spot here is actually the shadow of the parachute while it's coming down. And it bounced and it rolled and it bounced and it rolled and it rolled straight into a 20-meter wide crater. Tiger Woods on his best day cannot do this. They budgeted 5 trajectory correction maneuvers between the Earth and the Mars. Little chances to nudge the trajectory just a tiny amount. They only actually needed 3 of those, which means they came in at 2 under par, and that's why this is called Eagle Crater. All the craters around Meridiani Planum, where this is, are actually all named after vessels of exploration, and the Eagle is, of course, the spacecraft that first landed people on the moon. They opened their eyes, and this is what they saw. Bearing in mind, we're looking for bedrock, we're looking for rock in situ. Everything that Bonneville Crater was a failure, everything that they couldn't find with Spirit, they found right in front of their eyes. The very first image sent back by Opportunity covered this bedrock right here. This looks like pretty hefty stuff. It's, pretty small rover. The first images, they had to give a name for this feature. They called it the Great Wall. Once they got their images down and they can do stereo imaging and figure out what the terrain is actually like, great big rover, tiny little outcrop. This stuff's tiny. It's about this much. If you're wondering what this little bunny-shaped feature is down here, that's actually a piece of discarded airbags, a piece of ripped airbag material that they were able to watch over a few days and ended up being blown and hiding underneath the lander. They got out their mini thermal emission spectrometer and they went hunting for this hematite. And this is where they found it. This is red being lots of hematite, blue being none at all, looking overlaid on an image that they took. And in some places, there's very, very little. And in some places, there's absolutely loads. The places where there are very, very little is the same places where the airbags bounced into the soil. And so they took some pictures much, much closer of the ground and zoomed right in with their microscope. You can see there is soil, and the soil's got little balls on it. Little round, ball-bearing sized lumps of rock. They went up to the rocks over here, and imaged these rocks really up close, and you can see incredibly fine layering and these little balls pouring out of the rock like blueberries in a muffin. They nicknamed them blueberries because they're not that they're blue, but they're more blue than anything else around them. They took the instrument arm, went up to this rock. I apologise, there are graphs in my talk too. This graph's a bit of a mess, but all it really is reminds me to tell you that the difference between the soil and the rock is that the rock has got vast quantities of bromine and sulfur, both elements that are often found in rocks that have been deposited by water. Another horrible graph. This one is indicative of Gerra Site, vast quantities of Gerra Site within this rock. This rock is essentially sandstone. It's laid down in water. Then they got their microscope and looked at the morphology. This is the mineral. What's the stuff made of? Now, what does it look like? This is a patch of Mars about this big. And it looks like someone's baked a cake and then pulled out loads of 2p pieces out of it, little pieces missing. These are called crystal-formed growths, or vugs. It's where crystals formed within the rock when it was formed. Water has then come through and dissolved those little crystals back out again, leaving echoes of where they once were. At another piece of the rock, they actually mosaicked the thing. They wallpapered it with tiny little microscope images. And they could see the layering, but between the layers, little smiley features. You get these when you have running water. Imagine little ripples on a fairly calm beach. These are a fossilized version of that. So not only were these rocks formed in the presence of water, they were probably laid down in running water. The last puzzle was what exactly were these little balls. Unfortunately, the balls themselves are too small to be in the field of view of one of the instruments. So they took two spectra. They took one from a patch of rock that they called empty, and one right on top of the berries, and this six-pointed feature came out from their spectrometers. The berries are the hematite. And they're the kind of the third piece of the clue. They're hematite concretions, the conjecture being these rocks formed in the presence of running water, and then were soaked once again. And like an oyster forming, a pearl forming in an oyster, this hematite is concreted out of when they were re-soaked and formed these little round berries. You can find them on the Earth. They tend to be bigger on the Earth. Go to the Natural History Museum, you can actually see hematite concretions about this size. So 3 pieces of evidence. The case for water on Mars, signed, sealed, delivered. They made a complete mess of Eagle Crater, driven all the way around it, left their empty lander behind. At full resolution with this image, you can actually see the tiny little rat holes they drilled into these rocks. So mission accomplished. On a 90-day mission, and it's only Sol 48. Job done. What do you do next? Well, this is one very, very small crater. How about going to a bigger one? This is another image by Highrise, the amazing high-resolution camera in orbit. You can actually see the lander sat in the tiny Eagle Crater there. This is its parachute and the back shell discarded down here. And so they set out and drove across what is absolutely stunning rover driving terrain. And they drove about 800 meters to the east, towards this. This is Endurance Crater. This isn't Victoria Crater. This isn't the big one. This is medium-sized. It's about 200 meters across. This is what it looks like when you arrive. About 200 meters across, perhaps 15 meters deep. And if you remember the picture of the rover sat on top of a tiny little outcrop at Eagle Crater, this is actually a cliff. And it's a cliff. There's a massive printout of that cliff outside with anaglyph glasses if you want to see it in stereo. The rover is about that big. Tiny, tiny little rover on top of an enormous cliff. This is the place where if you're stupid, you can kill a rover very, very easily. And this is the picture they took right from the foot of that cliff. It took them a year, but they got all the way there. And not only did this confirm the story of water they'd seen back at Eagle Crater, but it added thousands, millions, maybe hundreds of thousands, hundreds of millions of years to the story of water on Mars. Much of this rock is actually laid down as sand dunes and then turns into rock, but it's all been made wet at some point following. So, Eagle Crater done, Endurance Crater done, about 360 sols into a mission. Where do you go next? You get bold once again. Here you can just see, that's Eagle Crater, that's Endurance Crater. Let's go for another big drive. For a 600-meter specified vehicle, they decided to travel about 7.5 kilometers due south to the crater that Jonty showed you, Victoria Crater. On the way there, they stopped off at a few interesting sites, one of them being this. A sure sign of intelligent life on Mars. Unfortunately, it's our intelligent life on Mars. This is where the discarded heat shield smacked into the ground, made a little crater, broke into two pieces and turned inside out. The heat shield was actually pushed away from the back shell of the lander by 6 large springs, each the size of kind of like a beer can, that sort of thing. And amateurs went hunting for them. We found them all. No one's stolen any of them. All 6 are still there. This is actually the inside of the heat shield. It's belly flopped and turned itself inside out. And to give you a sense of scale, you could probably just hunker down and hide underneath it. You can see there's a rock just on the far side. It's the only rock for hundreds of meters. It's not a rock at all. It's actually an iron meteorite. If you are looking for meteorites, Meridiani Planum is a great place to go. The tickets are quite pricey, but Steve Squires, the chief scientist, said that they clearly should get moving, as this is a place where large, heavy metal objects fall from the sky. They headed south, and they headed south very, very quickly. They put their foot to the floor. This was the picture taken at the end of the record drive, and it's a record that still stands to date. In one day, they drove just a fraction over 219 meters. Of those 219 meters, 110 were driven backwards and without intelligence. They just put it into reverse and gunned it. The following 119 meters, the rover did on itself. They just said, you've got this much time in the sequence, keep driving south as intelligently as you can. Look for hazards, drive a bit more. Look for hazards, drive a bit more. So the first hour, it covered half the distance. It took 4 hours to cover the remaining distance, but this, to date, stands as a Martian land speed record. And in fact, the gentleman who wrote that sequence recently came to visit the UK, and I met some colleagues of his in Coventry, and that is the Mars land speed record. I thought I'd give him some inspiration, and so I took him to see this. This gentleman is called Andy Mishkin. He worked on the Sojourner mission. This is his wife Sharon, who actually worked on Sojourner and the Mars exploration rovers. And this is Scott Maxwell, who holds the Martian land speed record. He's got competition because the car we're sat in front of has done 763 miles an hour, and if you may have just seen in the news, the guys who built this are actually going to try and beat their own record. It's extraordinary. Of course, driving this recklessly on Mars is eventually going to cause you trouble, and it did. I don't know how well you can see this, but these are the rear wheels, and they are buried up to the hubcaps and beyond in a sand dune. Here's a picture out the front. They were completely stuck. Here's the color picture taken of the same area. They just got slightly stuck into a sand dune, and then they spent... The rover thought, nothing in front of me, keep driving. Nothing in front of me, keep driving, for about 80 meters. And in that distance, covered only a few meters. These are 2 movies that cover about 11 days of driving. In those days, they commanded about 50 meters of wheel motion. And those 50 meters of wheel motion gave them about 28 centimeters of progress. This was terrifying. Eventually it gets better, and eventually, after about 2 months of trying, they got back out again. It turns out if you do get stuck in a Martian sand dune, the way to get out is to stick it in reverse and gun it. They didn't know, but they had to find out, and this is how you do it. After 2 years of driving, they made it to this Victoria crater that John T. showed you. And in fact, this was where the rover was when that colour image he showed you was taken. And they decided that they wanted to go in, but they didn't know where the best place to go in was. So they spent a year exploring the northern rim of Victoria Crater, all the way along the northern rim here. Whilst it was doing it, Highrise is still flying overhead, and took this picture. You can actually see the rover's tracks along the northern rim. You can see they explored between these, they called these capes, and they called these bays, from cape to bay, all the way around. And just here, they said, we've seen enough of Victoria Crater, we'll go into it now, and they started driving back again. Just here, here's the sort of views you get. This is again using that program called Midnight Mars Browser, written by an amateur enthusiast. It can reproject pictures back into 3D space, and you get a picture like this. This was called the drunken sailor walk, because the rover has nothing to reference. If you're on smooth terrain with perfect wheel tracks, there's nothing for the cameras to reference to figure out how far it's moving. They added intelligence to the rover to stop things like that June incident happening again. There isn't an actual way of detecting wheel slip. What you can do is say, right, I've just commanded a drive of 1 metre. How far have I actually driven by comparing pictures before and after? But on terrain like this, you've got nothing to compare with. So they put a little wiggle into all the driving so that the camera would be able to lock on to these little drunken sailor walking steps. This was the turning point at the eastern side of Victoria Crater. Literally and metaphorically, they actually used some of this new intelligence they'd uplinked to the rover and told it to get from here to here whilst avoiding this. It did so quite happily. Then they headed back to where they wanted to go in. And then Mother Nature intervened. These are pictures of the sun as seen by Opportunity over a couple of months. There was a global dust storm so bad that the sun was completely obscured from view. For a solar-powered vehicle, this is a bad thing. Colour pictures of the horizon, that's your average fairly dusty day on Mars. You got murkier and murkier and murkier and murkier to a point where, another graph, I apologise, this is how much power the rover was getting. And you can see a general pattern. Landed roughly in autumn, it drops during winter. It kind of comes high again during summer, drops during winter. And it's about to come high again during summer. The dust storm happens and boom. They were very, very close to losing the rover. Very, very close. But it just made it through. Drove into Victoria Crater and took pictures like this, showing more of this layered outcrop in these enormous cliff faces. The science from this isn't yet kind of determined, but it's going to be good when they figure out exactly what they've been looking at. This is a mosaic taken only a few months ago. Here's the route they took into Victoria Crater and then back out again. And they since left. This is the move they took on the way out again. You can see it's taken over a number of days, but in each of those days, you can see the shadows moving across the ground. So what next? They've travelled 7.5 kilometres. They've got 12 kilometres on the clock, heading south towards Victoria Crater, and they're done. Where are you going to go next? Well, you can't accuse them of being safe. This particularly low-resolution picture is low-resolution because it needs to be. That is the 7.5 kilometres they covered from Eagle and Endurance all the way to Victoria, and their plan is to do this. And try and get to this little thing here. This is called Endeavour Crater. It's about 20 kilometres across. It's about 15 kilometres away, but it's the right direction to go anyway. The terrain gets more interesting as you go this way. You're going uphill, so there's newer rocks as you go that way. They may or may not make it. The rover is more intelligent than it's ever been. The programmers are more experienced than they've ever been. But you've got to give them a round of applause for trying, if nothing else. I'm out of time, so I'm going to leave it there. I'll be very happy to take your questions. Stunned silence. Go on in.
Obviously, this latest problem with the dust thing took a while to recover from, did it?
Yeah, you're talking about that global dust storm. Yeah, that stole most of the last Martian summer. Opportunity got lucky that most of that dust didn't end up falling out from the dust storm onto the solar panels. Oh, yeah. But it took about 2 months. They were actually poised. They had a press conference and say, right, we're going to go into the crater. We know where we're going to go in, and we're going to go in next week. Next week happened. The dust storm happened. They didn't go in. In fact, they stayed in exactly the same spot for about 2 months, waiting for it to clear.
Because I was interested in the, before you said about that problem, how the eye in the sky, as it were, could see where the rover had been. I assume that the dust was continuous.
Yeah. That image, actually, the image with those tracks is actually about a few weeks before that dust storm occurred. If you look at there's a black and white print up on the boards outside, is actually the distance from Eagle Crater to Endurance Crater. You can see no signs of the tracks at all. They've been blown away. The fresher the tracks are, you've got more chance of seeing them. Once they're more than a few months old, they go away.
So it's literally waiting for the wind to blow the dust off
it's fingers crossed.
Panels every time.
It is fingers crossed. Maybe Mother Nature will help you. Maybe it won't.
Yes, all the broken rock that's on the surface of Mars there, I mean, it's all irregular. It's not worn smooth. Where's all that broken rock come from? It's scattered everywhere. Well, what's caused that?
Geologists tend to call it gardening. It's impacts. Basically, Mars has been without major erosional forces for some time. There is wind, and there is some scouring. If you look at the cliffs in Victoria Crater, you can see where scouring has occurred against the layering. But all this rock lying all over the place, especially in Gusev Crater, there's loads of rock lying on the ground. It's all ejecta from impacts. And if it's not ejecta from impacts, it's ejecta from impacts caused by ejecta from other impacts, secondary impact craters.
Right, thank you.
Is it possible to date the various rocks that you find?
Unfortunately, not yet. Engineers haven't figured out a way to put the sort of instrumentation you need to date rocks, which currently fills a pretty large laboratory, into a spacecraft where you've got about this much room. You can have relative age. You can say this rock is younger than this rock, but you can't say this rock is X billion years old. What we can do is date areas on Mars based on how many craters they have. A younger place will have fewer craters, an older place will have more craters. But there's no direct way of measuring the actual age of any one rock yet. It's going to take more engineering to figure out how to fit the kind of the carbon dating or those sorts of techniques, or radon dating or xenon dating into a very, very small box. You've got to fit a room into a shoebox, and they've not got there yet.
Hello. Maybe a speculative question. What's happened to the water? There's no evidence of hydrated rocks from what you've seen, but there's evidence of water action on volcanic rock formation in the past. No evidence of reflective poles, so there aren't glaciers around as far as we can tell. Could the water be below the surface, or has it disappeared?
They have found the water. A mission I didn't have time to say about called Phoenix, which landed this May and is still working to date, has actually found ice, and there's going to be it's epic quantities of ice just under the surface in the North Polar region, and the same is true probably of the South Polar region. A lot of it would have been lost to space. A lot of it would have frozen deep underground. But there are actually some hydrated minerals there. There are some of the rock formations they've actually measured have kind of a compound with NH2O in it. There's actually lots of water bound up in the rocks to the point where they see a water band within the thermal emission spectra. But most of it is probably as ice subterranean.
Is this working? I think it's off. Okay, thank you. If you could put any mission to Mars that you wanted within a reasonable budget, go anywhere, what would you choose to do?
Well, the next big mission to Mars is called MSL, the Mars Science Lab. And it's got budget issues, really big budget issues, like $1.9 billion budget issues. It's not the size of kind of like a small golf cart like these guys. It's the size of a Mini, as in a new Mini, the big BMW Mini, the huge thing. This thing weighs about 3/4 of a ton, and it is, to be honest, it's pretty much my ideal Mars mission because it doesn't have to rely on favors from Mother Nature to keep the solar panels clean. It has a large radioactive power supply on the back that will supply it with X watts every day for several years. Now, the landing site selection process for that is ongoing. I have my favorite landing site. It's one called Gale Crater. It's a crater about the same sort of size as Gusev Crater, but it has a huge central peak in which we can already see layered outcrops of rock, and there's a canyon that runs through the middle of this thing. And the option being presented to the mission selection board, as it were, is to land between the central peak and the edge of Gale Crater and drive through this canyon with huge kind of outcrops of eroded, exposed rocks either side. And I'd pay to watch that.
You said earlier that if there was no sunlight left, it would entirely die. Do they not have the capacity for it to restart itself when sunlight returns?
Yeah, I mean, it's the batteries have to be kept comparatively warm. It's superb batteries. The batteries on Mars Pathfinder back in 1997 died after about 90 cycles. The batteries on the two rovers have lasted about 1,700 cycles and are still going pretty strong. The problem is if you don't have enough energy to charge the batteries enough to use the heaters to keep the batteries warm, you end up freezing the batteries. Once the batteries are frozen, you can't charge them anymore. So even with clean solar panels, you're kind of a lost point. Now, that's why the best way to go to Mars is spend a lot of money to build a bigger rover that doesn't need them. The Phoenix mission at the North Pole right now is in kind of North Polar autumn, and it's north of the equivalent Arctic Circle on Mars. And so in about 5 months, the sun will set at the Phoenix landing site and will not be seen again for several months. And in fact, Phoenix will probably become buried in carbon dioxide frost to a certain extent. Now, the engineers know that this is almost certainly going to kill the vehicle, but they're not going to take the gamble of assuming it won't. So on board there is software whereby if it wakes up in the spring, it will try a Lazarus mode, try and charge its batteries and try and work again. And the rovers have similar software. If things go horrifically bad, keep trying until we tell you to do something else. But once you get to a point where you don't have enough energy to keep the rover alive on a day-to-day basis, it's unlikely you'll get it back at any point in the future. There's a question right behind you. Behind you was the one? No? I thought you asked one.
There was one further down at the front down here, then. There's a mic and a boom.
In view of the enormous success of the remote-controlled rovers, does there seem much real purpose in spending hundreds of times more money to send a manned mission to Mars with imminent danger to the people who go there?
I can give no greater advocate than Steve Squires, who is the principal investigator for the 2 rovers. He is a huge fan of robotic missions. And when the engineers and the scientists who drive Spirit and Opportunity were practicing, they had a rover like Fido, the old test rover, out in the desert somewhere in America. And they had some technical problems, and so the geologists just kind of said, right, fix the rover, we're going to go and do some geology. And they walked around and they did some geology, but Steve Squires didn't. He sat back and he watched. And he had a stopwatch and he had a notepad. And he wrote down how long it took geologists to do stuff. And it takes Spirit and Opportunity about a day to do something that takes a man about 30 seconds. Now, yeah, sending a man to Mars is a hugely expensive proposition. But there is a kind of a caveat to that, is that you can't spend money in space. It all gets spent down here on engineers and scientists, and it's good money to spend in that way. But the closing words in a kind of a pseudo-biographical book he wrote about these 2 rovers are that the thing he wants to see most of all is boot prints in his wheel tracks. So a huge expense, and so was Apollo, and we learn a huge amount from that as well.
If we could, I'll just stand back.
Yeah?
Okay. Firstly, can we thank Doug again for a superb talk? I really enjoyed that. Thank you.